everyone, welcome to this analog discussion session. So today we will be discussing some important RC and RL circuit, their transient response and their frequency response. Okay, so let's start. And we have Sammodi, Chundrima, Priyanka. Okay, today. So let's start. So I am sharing my screen. Okay. Okay. It is visible, right?
Yes,
Okay.
yes, it is visible.
Okay. So let's have a first circuit. Actually, we know all properties of capacitor and inductor, right? Both are called storing element. And capacitor store its charge as a form of voltage, right?
Yes,
And inductor store these charges or fluxes in the form of current. Okay, and we know the uh, capacitor resists the instantaneous change, the voltage change, like the instantaneous voltage change across it. Okay, so it resists sudden voltage change across it. Okay, similarly the inductor resists sudden current change, right? Current change across it.
yes, sir.
Current change through it. Okay, through it. So this is the basic property, and it is like this is valid when the current through the capacitor is finite. Okay, and this is also valid when the voltage across the inductor is finite. Okay, now question comes, if the IC becomes infinite and this VL becomes infinite, then the inductor can current can change instantly. Okay, instant jump. And if IC, like the current through the inductor becomes infinity, at that moment the voltage across it can be instant change, like there can be a sudden jump, or like the, I can say that like a sudden change. Okay, it can be increased or can be decreased. Okay, according to our circuit. So let's have a common circuit. Okay, so we all know the transfer function and the transient response of this circuit, right? If we have this input, this is a step of, let's say, 5 volt. Okay, step of 5 volt. Now i I will make a resistance here. Okay, let's say both, this is R1 and this is R2. Okay, now in this circuit I have to tell intuitively what will be the transient response and frequency response. Okay, for this circuit, for frequency response we know we need DC gain. Frequency response, we need DC gain and pole and zero, right? Okay, someone is trying to join, I guess. Okay, let me check. Yes. So so for frequency response we know DC gain, poles and zero, right? And actually in this session we are going to deal with the circuits intuitively. Okay, like we will not we will be not writing so many equations. Okay, okay. So now let's do for time domain response. Okay, time domain response. Time domain means transient response. Okay, and here we will be having frequency domain response. So this is the circuit. So so this is our t equals 0, right? And this is our t equals infinity. Okay, now for a step signal we know that the at t equals 0 plus, so at t equals 0 plus all the capacitor is short circuited, right? Hello.
Yes. Yes. Yes.
Yes. So all the capacitor is short circuited means the circuit fills a frequency of infinity. So the capacitive impedance is 1 over SC. So if this becomes S becomes 0, so this will be okay. So if S becomes infinity, so the impedance becomes 0. So 0 impedance means there is a short circuit, right?
Yes.
So now at t equals 0, the picture will be looking like the following. Okay. So so this will be the case, right?
Yes.
So what will be our V out here? So this will be nothing but 0, right? So this 0 volt is here.
Yes. Yes.
Okay. So at t equals 0 plus, capacitor acts as a short circuit because the signal frequency is infinite. So the capacitor impedance is 0. So this R2 plays no role because we know that if there is a two parallel resistance R1 and R2, so their effective impedance is nothing but like defined by the lower impedance, right? So this will be nothing but
Yes. Yes. Yes.
R1
Hmm.
R2 divided by R1 plus R2. Okay. So now if R1 is very less than R2, so the effective impedance is nothing but R1 itself, right? So if there is zero parallel some finite value, the impedance will be 0, right? So this is happening here. So now we have find that at t equals 0 plus the output voltage is 0. Okay. Now second case at t equals infinity. What will be the picture? The capacitor acts as a open circuit, right? Because the signal frequency becomes now 0. So xc will be 1 over sc and this is becomes 0. So this will be infinite. So we know that if a impedance is infinite, that means this is open circuit, right? So let's draw the picture again. So here we have R1. This becomes open circuit and this is R2, right? So this is our V and this is our V out. Now what should be the output voltage here in this case? Anybody?
It will be just a voltage divider,
Divider,
right?
divider rule.
Yes.
Yes, exactly. So it will be just a voltage
R2 by
divider.
R1 plus R2.
R2 divided by R1 plus R2 times V in.
Into V in.
Yes,
Into
Hmm.
V in.
yes. So this will be our output.
Yes, absolutely.
Yes, sir.
So we are taking V in as a 5 U2, right? 5 volt UT. So let's make this V in is 5. Okay. So this will be 5 times R2 divided by R1 plus R2. So now an on thing. So we have find that if we try to plot the response V out versus time, so we have t equals 0, our output is 0. So this will be the case. And t equals infinity, output is this value. So let's say this is the steady state case. So let's say this is 5 times R2 divided by R1 plus R2. Now question is what will be the behavior in this time? Okay, let's say this is our Tx. So can we comment the behavior of this like the response of it will be like linear or sudden jump or exponential? What would be that in this case? We know that
Maybe exponential.
in this circuit the
Exponential.
yes exponential because they are the current in this circuit is finite, right? So there cannot be a
Yes.
sudden jump. This is clear, right? And we know that when the time increases, when the like we are going from 0 to infinity time, When the time increases, the capacity's impedance become increasing, right? This impedance is increasing, capacitive impedance, and these two impedance are fixes. So the current through each branch is also not constant, right? This impedance is changing, na? So this current and this current will have to change. So this, like, the
Yes.
current in every branch is not constant as well, right? So the behavior cannot be linear as well, right? We know that if the current becomes constant, then the V out will be like this. So this becomes a linear waveform, right? If T increases, the V out also increases. So in this case, this is not possible as well, right? Because the current through each branch is changing with respect to time, right? So this cannot be happen as well. So basically, the waveform will be exponential here. Okay, and we all know that the, like, this is a basic RC circuit and the behavior will be exponential as well, right? We know that. If we
Yes.
write, if we write differential equation with respect to V out, we will get exponential solution, right? We all know that. So this is the time domain response. Okay, now question is, what can be the Tx so that the output becomes this voltage? So we know that if the time constant become, like, if T equals 5 times of time constant, then it reaches almost steady state. We know that, right? Right? Like, it will reach to this value at T equals infinity, but infinity is not possible, na? So it will try to make this to, like, what can I do, like 99.99%. Okay, it cannot be
Yes,
100%.
yes, almost reached it. Yes.
Okay, okay. So now we have to find the time constant in this circuit. Okay, to find this Tx time. Okay, so now to find the time constant, what we do intuitively, we like, we make all the independent sources inactive. Okay, and then find equivalent resistance and find equivalent capacitance, and the time constant becomes the equivalent resistance time equivalent capacitance, right? So to make independent sources inactive, so there is a voltage source, so this will be short circuited to the ground, right? Now, can someone tell what will be the R equivalent in this circuit and C equivalent of this circuit?
R equivalent will be R1 parallel R2,
Yes, yes,
and equivalent will be only C.
yes, because these two resistance comes in parallel, right?
Yeah.
So the equivalent impedance will be that, and there is only one capacitance, so this is C only. Okay, so what will be the time constant here? So tau will be, time constant will be R1 parallel R2 into C. Okay, now what will be the Tx value? So Tx will be nothing but 5 times R1 parallel R2 divide into C, right? Okay,
Yes, yes.
okay, okay. So now, can we comment the order of the circuit? Like, it is first order circuit or second order circuit or third order circuit or so on. It is a first order circuit, right?
First order, I guess.
Because there is only one storing element of C, like only one capacitor present. Okay,
One pole.
one pole system. Yes, this is called also single pole system. Now, if we do the frequency domain response, what we need? We need DC gain, right?
Yes.
What will be the DC gain in this circuit? At DC, what capacitor behaves? How capacitor behaves? Cap is open.
Capacitor
Yes.
is
Then
Certificate.
what will be the V out by V in at DC? So this will be nothing but R.
R2
By
R2 by R1
R1
plus
Yes,
R2
this is
into
the
V.
yes, this is the DC gain.
Yes.
Okay. Now what will be the pole location? This will be single pole, and we also know that in a single pole system the time constant is the inverse of pole. We all know that, right?
Yeah.
Actually, to find the pole, similar thing we can do, like all the independent sources are inactive, and then we find the R equivalent and C equivalent. Then our pole becomes 1 over R equivalent times C equivalent radian per second, right?
Amit, I have a question here.
Yes, 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 please, yes,
Is this true for only the fast pole,
yes,
one pole
yes,
system, or
yes, yes, yes. It is
what will be the problems we face if we try to assess this thing in multi-pole system?
yes, for multiple system we try to make the system as a single pole system. So we do the dominant pole like compensation, right, or Miller compensation, whatever it is. So we try to make a pole which is lower frequency than the other poles. Okay, and for multiple system we cannot directly comment the time constant. Okay, there comes zeta, like the damping factor, right? Hello.
Yes, yes,
Yes, so
yes,
there
yes, absolutely.
for multiple system there there is a concept of damping factor. Okay, from damping factor we can like comment the behavior in transient domain, like the time domain. Okay, so
Okay, okay,
for multi order system we cannot directly comment what is the time constant of the circuit. Okay,
okay, okay.
okay, so this will be nothing but 1 over R1 parallel R2 times
Into
C
C.
radian per second. Okay, please make this unit clear. Okay, radian per second. Okay,
Omega.
yes, omega. So we have pole, we have DC gain. Now we have to find the zero, right? Now first thing, is there any zero or not? By looking, how can we tell? So this is the circuit. Is there any zero in the circuit, or 1 0 2 0? Basically there are two like 3 4 5 different ways to find intuitively pole and zero. Okay, I am doing here like 2 3 cases. Okay, let's do it. So this was our circuit. So for zero, we know the V out will be zero, right?
There is no zero.
Yes, actually in the circuit there is no zero. So I am coming towards it. How we can we haven't any zero in this circuit. Okay, so we
Yes.
know
V0 will be grounded.
yes, V zero will be zero. So this will be short circuit to the ground. Okay,
Yes.
so is there any storing element here? Actually, this capacitor is
No.
short circuit. Like both of this terminal is grounded. So this becomes
Yes,
a
yes,
Yes.
dead element. Okay, dead
Yes.
element. So equivalent circuit will be looking like this. This is R2, this is R1. So this will be nothing but this.
Yes.
yes, yes.
So there is no zero, right?
There will be no effect. Yes,
Yes,
yes.
there is no zero present here. And we can also comment that from input to output, we can see that there is no extra path, extra frequency dependent path from
Yes.
input to output.
One path is here.
Yes, right. We don't have another frequency dependent path. We know that if there is a frequency dependent path from input to output, then that makes sure there maximum chance there is a zero, right? But in this case
Yes.
this is not happening,
Yes,
so
yes.
we can directly say that there is not a zero present. Okay, so how will be the behavior of the circuit in frequency domain? Like the if we draw the Bode plot, Bode magnitude plot. Okay, this is Bode magnitude plot, and this is our omega. So this is a DC gain. DC gain is key,
Yes.
R2 divided by R1 plus R2, and this will be in dB. Okay, I am not writing that. So this will be 20 log of this. Let's say this is H of S. Okay, and there is a pole, let's say this, and this falls minus 20 dB per decade slope. So this is our omega p on. Okay, so this is the thing. Okay.
Okay.
So,
Yes.
and if we try to draw the phase plot, so this is angle of h of s. So let's say this is 0.1 of omega p on, and this is 10 times of omega p on, and this is omega p on. Okay, we know that for a like phase response, it feels like okay, let me do. So from here it feels a change, right? Then it goes to minus
Yes.
45 degree,
Minus 45 degree.
and then eventually it goes to
Minus
minus
90 degree.
90. Like it cannot goes to minus 90, it goes minus 90 at it,
89
so
point
it will be,
something.
let's say, minus 89.9, so on. Okay.
99.
So this is the Bode phase plot, and this is Bode magnitude plot, and this is Bode phase plot. Okay, so this circuit is clear, right?
Yes.
Like we have analyzed this circuit in like in many ways, right? And
Yes.
except noise, this circuit is discussed very in a well manner. And so which type of filter is this circuit? Can we comment which type of filter?
Low pass filter.
Yes, basically this is a low pass
Yes.
filter, right?
Yes.
So we can see that at low frequency the gain is more, and at high frequency the gain is almost, so this is 0 dB, right? So gain is less. So basically this is a low pass filter. And intuitively we
Yes.
can also see that we can, if high frequency, at high frequency this capacitor is shorted, right? So
Yes.
the gain is 0, right? So
Yes.
at high frequency the gain is 0, so this cannot be a high pass filter.
Pass
But at
filter.
low frequency it can transfer maximum amplitude, maximum power, right?
Hmm.
So this is how we can also look at it. Okay, this is a low pass filter. Okay, so so this circuit is okay. Now I am drawing another circuit. Okay, acha, okay, let me draw a inductive circuit. Okay, huh? Inductive circuit. Okay.
Okay.
Okay, can anyone comment which type of filter is this?
I guess high pass filter.
You are saying high pass filter. Okay, let do that. At high frequency, at high frequency okay, at a high frequency, what will be the capacitor inductive capacitance, like inductive impedance? So this will be infinite, right?
Yes. J
In,
omega L.
infinite means this is open circuit.
Hmm.
Then what will be our V out?
This broke down that.
V out will be 0, right, at high frequency.
Yes.
Yes. Yes.
So like, is this statement true?
No. No.
Okay, let
In
me
high
make,
frequency, we are getting zero voltage, right?
yes. Okay, let me
So
Hmm.
how
make,
can it be?
okay, let's make another thing. So at, let's say, zero frequency the inductor is short circuit.
Hmm.
Yes.
Now what will be the V out here?
V in.
V in.
Yeah.
Then here what is the gain, and here what is the gain? Here the gain is 0,
Again is
here the gain is 1.
here.
Then which
One.
type of filter is this? This is a,
This should be a
Low.
low pass
Low
filter,
pass
right?
yes,
filter.
yes, this should be a low pass filter, right?
Yes. Yes.
Hmm.
And what will be the pole frequency? First thing, Is it a first order circuit?
Yes.
Yes, first.
Yes.
Yes, this is
Why?
first
Why?
order.
Why?
There is only one current storing element in the
Yes, yes. This is a first order circuit. And what will be the time constant of the circuit?
R
R
equivalent
by
and
L.
L equivalent divided by R equivalent. This is the
L
time
by L
constant
by
of a
R.
LC circuit. So L is nothing but
Yes.
L itself and R is equivalent R itself, right? This is
yeah,
second. Okay. For inductive circuit, if we try to find the time constant, we have to find the equivalent inductance and equivalent resistance. Then we have to do L equivalent divided by R equivalent. Okay. Now what will be the pole location here? So we know that in a single pole system, time constant is the inverse of omega p1, right? Pole location. So this will be nothing but R by L, radian per second, right?
Hmm.
So this is a basic low pass filter with inductor. Okay. Actually, why we are not talk about inductor so extensively? Because in the indicated circuit, to make a inductor is very complex, and to make a high value inductance is also complex. Okay, so we are dealing with capacitor only. Okay, at mid range, at mid range frequency. Okay, so we are always try to do the capacitive behavior of the circuit, like the analysis we using capacitance. Okay,
yes.
so now let me draw another circuit. Which type of filter it would be? B is a step.
Opposite circuit it
Yes,
is.
this will be high pass filter. Okay,
Yes.
like at high frequency, this is open na.
Hmm.
So V out becomes V in. So the gain is on, like the maximum gain can be
Yes, yes.
possible at high frequency. Okay.
I think.
Okay. Now what would be the time domain analysis of this circuit? So this will be also exponential, right? Okay, let me do. At t equals 0 plus, at t equals 0 plus, what will be the case? This is short circuit, right? Because the XL is 0. Like this is SL, na? So if this, like, oh, sorry. At t equals 0, the frequency is infinite, right?
Yes.
So if this frequency is infinite, the
Yes.
impedance is infinite.
Yeah.
So
Yes.
this becomes
It
infinite.
open circuited.
So this
Open
output
circuit.
voltage reach there, right? So
Yeah.
V out is 0.
Yes.
So this is our 0, right? At t equals 0. And t equals infinity, our frequency becomes 0. So 0
Zero.
means this is short circuit,
That
right?
is short circuited. Yeah.
So V out becomes V in. So this, let's say this is V in. Okay. Let's say this is 5 of a step of 5 volt. Okay. And the behavior is, we all know this will be exponential, right?
Hmm.
So this is the time domain behavior. Like this is a very normal and like very basic circuit. Okay. And this is the frequency domain analysis. Now, okay, make another circuit, very interesting circuit. Let's make this. Okay, we previously we have this circuit, right? First circuit, right?
Yes, yes.
So now if we make this, what will be the changes in the behavior? If we can make this. This
It will
becomes
introduce another zero, or
yeah,
1 0 at least.
yes.
Uh,
This makes a zero. Okay, let me do the in a quick manner. Let me draw the transient response and frequency domain response. Okay. What do you think at t equals 0? the circuit behaves. So t equals 0, the circuit becomes this, right?
Again, V out will be the voltage divider.
Hmm? Which type of voltage divider? Resistive or capacitive? This is the question.
Resistive. G is equals to 0 means F is equals to infinite. Capacitor will be at short
Short circuit.
circuited.
So this will be the picture. But is this possible?
Yes, yes, yes.
Where
This
is the
this node
resistors?
this node is going to here. So this makes V out is 0, and this is also circuit. So this makes the V out is 5 volt. Is KVL is satisfied here? And what is the current flowing through this branch at this condition? This is infinite, right?
Yeah.
Why infinite? Because
Yes,
we have,
infinite current.
yes, we have no resistance, right?
So, okay. So
Okay.
it is introducing a zero.
Yes. So what we'll do? In this case, the capacitor can change its potential suddenly, right?
Yeah.
Yes, yes.
Okay. Okay. Let me make this is VC2 and this is VC1. Okay. So let's say this is V out is VC2, and here we have VC1. Okay. So now, and how the voltage can be settled here? So there will be a normal capacitive divider. Why? Because these two impedance is less impedance than these two, right? At t equals 0 plus. So there would be this C1 and there would be this C2, right? Okay.
Can you explain it, Amit, a bit again?
Okay. Basically, we are seeing that at t equals 0 plus the circuit becomes this, right? But anyway, is this possible?
At t equal to 0 plus.
Yes.
Hmm?
This is 0 volt.
No, this is not actually practically possible. Hmm.
KVL is not valid here, right? Like
Hmm.
one
Hmm.
node should on potential, right? But here there is two potential. One is ground and another is 5. This is not possible, right?
Not possible.
Yes. So basically here the current is flowing infinite in this circuit, like in t equals 0 plus.
Yes.
And actually we
Mm-hmm.
are we are talking about that the capacitive impedance very less, but there is like capacitive impedance, right? And that
Hmm.
is that is decided by these capacitors only. There is no, like, the R1 and R2 is playing nothing at t equals 0 plus to this circuit. Understand? Because they are two comes in parallel, right? And this impedance is very less than this, and this impedance is very less than this R2. So only there is two capacitor present equivalent. Okay.
Now got it, Amit. Yes.
Okay. Now
Okay.
now the voltage will make them in capacitive manner, capacitive divided manner, right?
Yes, yes.
And in this case the voltage across this capacitor will be sudden jump. There will be sudden jump. Okay. Like suddenly they can changes the potential across it. Okay. So this is the main thing here. Okay. We normally know that the capacitor cannot change its potential suddenly, right? But in this case we are saying that the current is infinite, so the potential can be changed suddenly. Okay. Now what will be the VC1? So VC1 will be nothing but C2 times 5 divided by C1 plus C2, and VC2 will be our V out will be nothing but C1 by C1 plus C2 times 5. Okay, right? Okay.
Yes.
So this is the normal capacity divider, we all know, like the opposite of the resistive divider.
Yes.
So now the V out will suddenly jump from 0 to this voltage. Okay, this voltage. Okay, let's make this clear. Simplification, C1 becomes C2 becomes C. Okay, so now this 5 volt will divide it into 2.5 and 2.5, right?
Hmm.
Okay, is this okay?
Yes, yes.
Yes,
Oh,
yes.
okay. Now and we are assuming there is no initial charges across C1 and C2. Okay, it is clear, right? This CO2. like the C1 and C2 are initially uncharged. Okay.
Yes, yes.
Okay. Now this is happening at t equals 0, and the capacitor, like the voltage across the capacitor, is changing suddenly. This is clear. Now at t equals infinity, okay, let make here. Capacitive impedance is infinite, right? Then what will be the equivalent picture? This will be the equivalent picture, right?
Yes.
Because
Yes, yes.
capacitive impedance is very high. So basically it is neglected, right?
Yes. Yes.
So then again it will be nothing but a resistive divider, right?
Yes.
Right? So at t equals 0, or like at t equals infinity, the V out will be nothing but what? R2 divided by R1 plus R2
Plus that
times
too.
5, right? And what will be the VC1? VC1 will be this, right?
C2 by C1 plus C2.
Why C2?
PC1.
VC1 will be, this is the polarity.
Okay. 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 In
So
this
this will be nothing
case.
but R1 divided by R1 plus R2 into 5, right?
Uh,
Now the question is, if R1 becomes R2 becomes R, then what will be the V out? 2.5, right?
Yes, 2.5.
And this is also 2.5. So the circuit will behave like this, right? So it will be like this, right?
yes.
Now which type of filter is this?
All pass.
All pass filter, right?
Mm,
Yes.
So let's say we are not going to do this here. So not make R1 becomes R2 equals R and C1 becomes C2 equals C. Okay. Let's say this potential is higher. Okay. Like the capacitive divider voltage is higher than the resistive divider potential. Okay. So this will reach some voltage like this. Okay. Let's say. So this will be like this. Okay. Right.
If we consider that actually.
If you consider that, and what will be the VC1? VC1 will increase or decrease? VC1 will decrease, right?
Hmm.
To make KVL, like to make KVL satisfied every time, right?
Yes.
Okay. Like in this case, I am making R2 is very large. Okay, nothing else. So here R2 is very greater than R1. Okay. Okay.
Okay.
Okay. And okay, condition is so the overall circuit will behave like this: C1 equals C2 equals C, and R2 is much greater than C1 R1. Okay. So the overall picture will be looking like this. Okay.
okay.
Okay. Okay. Why this VC1 voltage is decreasing? So make some interpretation. Okay. So actually we know the at steady state the VC1 will be this, right? Right.
Yes.
Yes.
X equal to infinity.
Yes. So R1 is very less than R, like R1 is
Mm-hmm.
very less than R2. So this will be nothing but 5 by almost, let's say, infinity, right? So this will be 0 na.
Yes.
So this is the case. This is happening. Actually, this capacitor is discharging. Okay, nothing else. Like it, both of the capacitor is charged to, let's say, 2.5 volt at t equals 0. Then this capacitor is discharging and this capacitor is charging more. Okay. Okay. Hmm. So basically, interviewer may ask you, like giving these conditions. Okay, R1 is greater than R2, C1. Like there are three conditions, right? R1 C1 is greater than R2 C2, R1 C1 equal to R2 C2, and R1 C1 is less than R2C2. Okay, and then they will ask you the transient response and the frequency domain response. Okay. Okay.
Mhm.
Okay.
Okay. So how much time? Okay.
324.
Okay, let's do another 20 minutes. Okay. So now another important circuit I am giving. Okay. Okay, let's. So if we do a current input here, let's say 5 amps. Okay, and this is the time period. This is RC, and we have to plot the V out versus time. So what will be your approach? Can anyone tell something? Like how can we go for the solution?
Zero.
So yeah, let's say analysis should start from t equals 0 plus, right? So at t equals 0 plus to t by 2. So this is t by 2. Okay. So at this time period, the current is constant, right? In this circuit, right?
Yes.
Constant current of 5 ampere. So
Yes.
if we have a constant current through a capacitor, then what will be the output voltage? This na, and the
Yes.
nature of the output will be
Yes, yes, yes.
a ramp, right? So at t
Please
equals
repeat again.
okay. So okay, we know that the voltage across a capacitor is nothing but the 1 over C integration of I C dt, right?
Exactly.
And we are considering this capacitor is independent of time. Okay, we have to consider this, right? Now if this is constant, so this will be out of the integration,
Yes.
and the integration of dt is nothing but t.
T.
So this is the thing, right?
Yes.
So now if time increases, the voltage across the capacitor will also increase. Let's say this is t by 2.
Yes.
Now what happens after t by 2? So this is so the circuit will, okay, let me do that. So now what will be the current through this time?
Zero.
Zero current. So zero current means this is open circuit na.
Yes.
So open circuit, is there any current flowing through this path?
No.
No. So the capacitor can charge. Can the capacitor be charged?
No.
Can be discharged?
No,
Mm.
Can the
no,
capacitor?
there is no path of this
Yes.
Yes.
So the
discharging.
capacitor cannot be charged and cannot be discharged. Then what the capacitor will behave? So it will hold its previous voltage. That is this,
Yes.
right? So
Yes,
let's say this is the case. Now, what will be the case at t t? Okay, okay. 3t by, okay. So this will be nothing but t plus t by 2. So this will be 3t by 2, right? This point. So t
yes,
t2 3t by 2. What will be the picture? There is again a constant current of 5 ampere, right?
Yes.
We can see that
yes,
this is a 5 ampere. Then the voltage across the output will also ramping up, right?
Yes.
yes, yes.
So question, it will start from 0 or it will start from its previous voltage? This is the question.
I guess this is T. You draw.
right?
Yes, yes,
Yes.
the T.
So question is, it will start from here ramping up or start from there? So it will start from there only, right? Because it has the capacity to hold its previous voltage, right?
Mhm.
Yes.
So then it
So I think
Absolutely.
it will continue, okay, like this. So there will be a staircase, okay,
okay.
okay. And how much the capacitor can be charged? Like what is the limit of the BC? Up to dielectric breakdown, right?
Yes, theoretically it is.
Like if we
Mhm.
do for real circuit, okay. So let me do another circuit. Uh, let's say, okay, which okay, let's another circuit. This is input, okay. So what is the input here? This is a
Ramp,
Ramp.
ramp
yes.
input.
We have ramp input and we have to make the output plus versus time. Then again
So
we
there
have
is
to,
no constant current flowing.
yes, this is sure.
Absolutely. Mhm.
But at, okay, the hot capacitor does it integrates the current through it, right?
Yes.
Capacitor integrates IC, right?
Yes.
Now let's make T equals 0 plus. So at T equals 0 plus, the capacitor is short circuit, right?
Yes.
So the voltage will be 0, right? This voltage reaches there.
Yeah, yeah.
Now and T equals infinity, capacitor is
Open.
open circuit, right?
Yes.
Open circuit V
T
out,
is equal to infinity, capacity to be open circuit.
yes,
Mhm.
because this signal carries all frequencies from 0 to infinity, right?
Mhm.
Huh. So this will
Yes,
be
yes.
open circuit. So the now V out will be V in, right?
Yes.
Because this becomes this, na. So V out equal to V in, right? Hello.
Yes.
Yes, yes. Mhm.
But actually this is not happening here, okay. This is wrong, okay. Why wrong? I am telling. So we know that at T equals infinity, the capacitive impedance is more, right? Like the capacitive impedance is very, very high, right? Right?
Yes.
So
Yeah.
what capacitor will try to do? It will try to drop maximum voltage across it, right?
Yes.
At T equals infinity. I am telling again, at T equals infinity, the capacitive impedance is like more significant, like the larger impedance in the circuit. So the capacitor will try to drop all the input voltages across it, right?
Yes.
But here in this case, we can see that there is a ramp input, right? Right?
Yes.
Yes, indeed.
So V out will be try to be ramp as well.
Yes.
But when it is possible to the voltage across the capacitor becomes a RAM. When it is possible?
When it is charging the capacitor.
Charging through a constant current, right?
Yes, charging through a constant current.
So IC becomes constant, right? At t equals very greater than 0 time, right? Like infinity, we can say, right? Now the thing is, if IC constant, right? So there will be a finite drop across this R, right? Is it right or wrong?
Yes.
You get my point, right? The capacitor want to drop all the voltages across it, but the input is ramp. So when the capacity, like the when it is possible to have a ramping voltage across a capacitor, when it is possible only when if the capacitor current is a step or
Constant.
constant, right? So if there is a constant current flowing through the capacitor, then it should flow through the R as well, right? Because this is a closed path,
Yes.
right? This is a closed path I. Like, oh, this will be this. So this will be a voltage. Okay. So this is a closed one, na. So the current flowing through this capacitor will have to flow this through this resistance as well, right? So there will
Yes.
always be a drop across this resistance ICR. Then what is the voltage? Like if we try to make a KVL, so V out will be nothing but V in minus I into R, na, right?
Yes.
Everyone get it, na?
Yes.
Yes.
This is V in, na. So I am writing V in will be nothing but IR plus V out. This is grounded. So V out will be this.
Mm.
So we can see that there will be a always a steady state error of this IR drop. So now if we go to the picture again, so actually this was our input, right? And we have a steady state error
Yes.
of IR. So this will be our V out, okay? So this voltage is IR voltage, okay?
Okay.
Now question is what will be the nature from this, let's say T1 to T2, like in the mid range time, okay? Can we comment what will be the nature of this waveform? Like we have 0, t equals 0, we have 0. We have t equals infinity, we have a V out of RAM, but there is a steady state error of IR, okay? So this difference is IR, okay? This width, okay? Now my question is, what will be the nature at this time? Like this will be, like if like this can be go to this, or this can be go to this, or this can be go to this, or this can be go to this type of I am asking, okay? So let's make it, okay? Now we know the capacitor indicate the current, okay? Now at t equals 0 plus, what is the current? Current is nothing but V in by R, right? Because the capacitor is shorted, right?
Yes. Yes.
And this current is indicating, like this will be the VC, right? On over, right?
Yes.
Now we can see that the VT, sorry, this will be, okay, this is I, okay. So now we can see that actually what is the indication of RAM? Can we directly comment?
Simple.
This will be parabolic shape, na.
Simple.
Parabolic.
This will be parabolic, like x square term will be there, like square, right?
Okay.
There will be a square law.
Yes, yes, yes.
So now if I actually mathematically if we do that in this time duration, we will be finding there will be a tx square term. Okay, so this will be a parabolic shape. Understood?
Ah,
So this will be this. So
Okay,
there
okay.
will be a parabolic shape here. Okay, like you can do the mathematics as well. Okay, let me do once. So current is so V in is also changing with respect to time, right? So can we okay? So if we do V in is nothing but some let's say 1 into t. We can make this na. This is the ramp function. So Vc will be nothing but 1 over c integration t into yes. This is happening. So if we integrate this will be t square term, right? By something. Somebody.
Yes.
So
Mm-hmm.
so this implies there will be a parabolic shape for a small duration
Yes.
of time. Okay. So this is a small duration of time. Okay. So there is a parabolic shape and there is a ramp and this is almost zero or we can say maybe like it follows the v like zero voltage. Okay, at this moment. So this is how the circuit will behave. So the output will be looking like this. Okay, so there will be at steady state error. Okay,
hmm.
basically this is a very important circuit and we are solving this intuitively. Okay, if you do the mathematical calculation there will be some results similar to this. Okay, okay.
Yes.
Actually, we are first not writing, so V in will be nothing but let's say 1 into t, right? This is the ramp function, na? So I
Yes.
am just
Hmm.
putting this V in voltage there. So there will be a like, indication of this, and there will be a term of square t square. Okay. So
So
can we stop
can
here?
we stop here?
Yes.
Okay.
Yes,
Yes, yes,
yes.
yes, yes.